Ellen Coley and Warren showed that in Warren grad school.
Good. It's the guy put up there.
All right. So a couple I know are out sick, something like a flu or something, so something's going around. So be careful. Get the flu shot if you can, or wash your hands. But today we'll talk about 2A ANOVA. Primarily we'll look at the 2A ANOVA with replication. So you have possibly more than one observation of each combination of treatment levels. We will talk some about chapter 14 without replication. When you only get one, there's limitations to what you can do when you do that. But it's often a design that would be used if there's limited resources. You get kind of as much information as you can, but there are some challenges with estimating variance and things. You don't have replication, but we'll see more about that. So there's 2A ANOVA. There's two different factors being considered. Two different factors affecting the outcome Y. So just some brief, examples. Of the type of things that can happen. You can have two factors you can manipulate. So let's say you're looking at, you can have, several markets. That's what I wanted to say. Say you have several markets. Right? And so the different markets where you're going to be selling things are in units. So every town, every place that has a certain type of grocery store, things like that, could be a market. And you can have some item that you're selling, and you can manipulate the price. Bananas, 59 cents, 69 cents a pound, 79 cents a pound, or something like that you're trying to sell. And maybe you're doing some type of promotion. You could have no promotion, or maybe you do a promotion on the radio that you talk about the item that you're selling, or maybe you put something in the newspaper. And of course, you could have other promotions. You put something on buses, right? Billboards or something. All right, and so you have a couple factors, and you could be interested in the price that's being offered there, and the promotion. And if the markets are far enough apart, they might kind of have be slightly independent of one another, but you could run into a problem that radio goes for a long distance, so what you do in one town might affect the others, and so on. So we could have a couple treatment factors and an outcome. So the outcome would be some amount of sales, or maybe sales relative, adjusted for size, because sales are naturally bigger in some larger communities. So sales might be adjusted for size. And maybe there's some type of interaction, right, between these as well, that a smaller price advertised more heavily might really boost sales, more so than just having an average price or just the type of advertisement. Maybe advertisement doesn't work if you're at a higher price, and so there could be this interaction that you'd be interested in finding the optimal spot to do that, right? So that'd be kind of one example. A second example that we'll look at, kind of building up a simulation of things, is we can have an outcome here. Say you're looking at some type of strength of steel bars, right? So in manufacturing, you make your bars of steel or some component, the hull of an aircraft, or a car, or a building frame, and you want it to be strong. So you're putting the raw ingredients in, the different treatment factors that you could imagine for this. There could be low or carbon levels in the manufacturing process. So you get the inputs that either have lower or higher carbon levels. The steel can be made it has to be made at a pretty high temperature, but there's high temperatures and then just ones that are lower than that. And there could be some interaction possibly between the carbon levels and the temperatures, and you can manipulate both of those things in the interaction and see if a particular setting really impacts the level of steel. You wouldn't necessarily be limited to just two. There could be medium levels, or the carbon levels or temperatures could be more quantitative. So it kind of blends into, would you use a regression to analyze it, or is it just these levels of ANOVA that would be there? Right. But it would be also useful in other contexts where you can't really randomize an experiment, right? Say that the Y outcome is, the purchase price of a new appliance. Right. What's the new price of the television that somebody is buying? What impacts somebody's purchase price? You could do a survey where you have customers that have bought something and collect their data, but what affects that? Well, one variable that could affect that, right? So X1 could be something like family income. People are often hesitant to put their actual income dollar value on forms. So you ask them, what's your income? If they have particularly high income or particularly low income, they might not like to put the dollar value. So sometimes these surveys ask in a range, or less than 35,000, 35 to 50,000, 50 to 75, maybe over 75 or something like that, for the purposes of buying a new television. That at a certain point, the income, as it's getting higher, it doesn't kind of matter that it's $100,000, $200,000, $300,000, right? It does have probably an impact, something like that, but you might be willing to have four ranges that are kind of moderate at on the upper end, and that would be enough to say kind of it's high enough that somebody might be considering the higher levels. Another thing that might impact this is family stage. And that might have a number of levels as well. So what could be some levels of family stage? That somebody the family is younger and they have no kids, or the family's older and they have no kids at home, or they have children at home, or they have kids but they're not something like that, right? That could impact some things. So it could be related to certainly purchasing some things, right? And if there's kids at home, and what capacity or size of a washing machine are you going to buy, or a dishwasher? There's some, or refrigerator size, or there's some impact of that. So the family stage might be measured in some way. And those are things you really can't randomize, but they're factors that would reasonably impact that. And so, two-way ANOVA would look at this, what affects the outcome, and maybe is there an interaction between different factors. Analysis of covariance throws in a quantitative X along with different factor variables. So you can study that. Right? And so in thinking about two-way ANOVA, one thing we want to think about today is what do effects and interactions look like? How would we see them? Right? But one thing we can do is look at the means within groups. Right? So thinking about the carbon example, if you had something like, say this is the low carbon and high carbon levels here, or a couple levels, and we're going to have, the strength, some measurement of braking strength, a Y value variable up here. I'm going to put a couple averages in here. Say these are the two averages when we use high temperature. And I don't know the engineering to know whether this would be really accurate or something like that. So some people put two things there and sometimes put a line there. That the line doesn't really indicate much. It just kind of might help visualize that these are the averages at this other level. Right? And if there is an effect also of temperature, maybe the low temperature annealing to make the steel would produce averages that are kind of like that. And if these are the averages, the Y-bar averages at those different levels, there would appear to be a temperature effect. Right? Is there much of a, maybe less of a carbon effect, but this one's lower than that one, but maybe not as much. So you kind of get the magnitude of the effects there, kind of illustrated. And if these are roughly parallel, and you could switch low temperatures here and high carbon up here, and it would change how the graph appears, but you would still, sometimes you can see more of a difference if you do it one way versus the other. Right? But this one graph would suggest that there's really no interaction between, in effect, between the carbon and temperature, right? Because these are roughly parallel. Right? If there were an interaction, you would see some other graph, right? So you could see, there's a big difference here and a smaller difference here. You would see an interaction. So this would suggest that the high carbon, low temperature really increases the strength relative to just having low carbon or high or low temperature or high carbon. But the combination gives you something extra. Right? And other interaction plots, if they're there, you could have a reversal where one level of one variable is good with another one, but it goes the others. Right? And some of the diabetes studies, as people get older, and as males, females have different hormones and go through different changes, then the benefit of exercise versus drugs kind of changes as people age and depending on gender, right? So there can be kind of an interaction about which is good. And of course you could have something where they start out different, and depending on how you picture it, they could come back together. So at a certain range, there's a price difference might make a bigger impact on low-income customers versus high-income customers and things like that. Right? To look at this and think about what the ANOVA calculation would look like. So these are all possible where you would see an interactions. Okay. Now, of course, these are also just means, so there's variability on there. Any of these pictures could be significant, and any of these pictures could be non-significant, depending on how much variability there is in Y. Right? If each of these box plots would be this massive range based on a small sample size, nothing's going to be significant, right? But on the other hand, if you have a larger sample size or narrower variability around each of these points, anything can be significant. It all depends on that relative mix of things, right? So let's look at a numerical example to build up one of these things to see how things go. Right? Let's say that the average strength is 100. And there'd be some units there, right? So for instance, in the middle schools, there's a bridge building activity, right? Maybe in Chittenden County, where they try to build bridges out of popsicle sticks and glue, and they have to be a certain distance and have to be a certain height. And in the final evaluation, they put them under a crusher. And they press them until they break. And some of these things stand up to fairly good amount of weight. Others just crumble with the slightest pressure, or they kind of falling apart, putting them down on there. Right? So anyway, so you can measure average strength through a number of ways, right? And let's say that the low carbon effect is to reduce, reduce it by 1, and the high carbon effect is to increase the strength by 1, right? And the low temperature effect is to increase the strength by 2, and the high temperature effect is to decrease it by 2. Kind of these additive effects add up to 1, right? So then our plot of what this would affect by. So if we put low carbon here and high carbon here, right? So at low carbon with low temperature, we'd be up here at 101. So this is going to be low temp, and high temp is going to be less than this. So low carbon, low temperature is going to be 97. Right, taking the 100 plus the 2 adjustments. And then this one is going to be at 99. And this one up here is going to be at 103. And as it's set up, with no interaction, they'd be parallel, right? So we get that graph. Now let's imagine that we put in individuals per group, right? Whatever n is, 1, 5, 10 per level, right? So we'd have 4 times n subjects. We're going to n per group, whatever n would be. And there's also a variability. Right? There's an error variance around those means. Let's say sigma squared is 4. So that sigma equals 2. Right? So that's the standard deviation of the y errors about that. Right? What is our ANOVA table going to look like this, when there's no interaction present at all? We're going to fill in our ANOVA table based on this example. There's going to be a sum of squares for carbon. This is the carbon one, yeah. There's a sum of squares for temperature. There's a sum of squares for interaction. And then there's error and total. Well, those are really the sources. There's sum of squares, degrees of freedom. Right? So if there's n per group, right, then there's 4n minus 1 total. Right? For carbon, there's only 2 levels of carbon, so there's 1 degree of freedom there. There's 2 levels of temperature, so there's 1 degree of freedom there. There would be 1 degree of interaction, right, even if it's 0. So how many degrees of freedom for error? Well, there's 4 per group, right? And so there's kind of n minus 1 in each of these 4 groups. So 4 times that is 4n minus 4. And these things add up to that. Right? What is the sum of squares due to carbon? Right? So there's 4 groups, and there's n in each group. And the effect, the difference of the carbon mean versus the other mean in every group is either -1 or +1. Right? And so there's 1 squared. Right? So it's actually 4 times n. You might do this. There's 2n of the subjects get low carbon, so that's 1, and then 2n of the subjects get -1, and so it's 4 times n. The carbon sum of squares is actually 4 times n, because the difference between the carbon mean and the overall mean is ±1. Right? Now the sum of squares for temperature, right? That was ±2 for each one. So the sum of squares for temperature, well, there's 4n subjects, and the average difference of the mean relevant for them in terms of temperature is either ±2. So it's going to be 2 squared. So there's 16n that's there. As it's set up, there's no interaction. Right? There's no change. And if it really fits that, it's going to be like that. Now, what's the error going to be approximately? Right? So the sum of squares error is going to be something like n minus 4 times 4. Right? Now why is that? The expected mean square error when we do our estimation is supposed to be sigma squared, which we're saying is 4. Right? And the how would you calculate that mean square error? Well, that's going to be the sum of our individual points minus the average in their group squared. And we would divide by the degrees of freedom for this. 4 times n minus 1. That we would divide by this degrees of freedom to get this. So 4n minus 4. Let's see. Let me just erase this to make sure till I'm sure that's what I want. Right. So we should have something like 4. That this sum of squares here should be something like this times something about 4. So it looks like it should be 16. Oh, I see. I was just reading the wrong column. It should be like 16n minus 16. If you add all those things up, our total sum of squares should be 4n minus 16. So under this simple scenario, you can actually go through and see what these should be like. Right? That's 4n minus 4. Multiply this, so it would be 16n minus 16. Right? What do our mean squares, what should they look like in this scenario? Obviously, we're just going to divide. Yeah.
How do you get 20n?
So adding the, oops, I'm not sure.
Isn't it 36n?
Yeah, it should be 36n. 36n minus 16. I think my notes were wrong from before. I see what I did. So yeah, if you add those up, it should be something like that, right? It's going to depend on the sample size, but by specifying the other things, you get something like that. So what do our mean squares look like? Well, this should be 4n and 16n. This one should be 0. And if you divide the sum of squares by degrees of freedom, you just simply get 4. Right? And so what are our F statistics going to look like? Right? So we're going to use this as the denominator for all of them. So dividing the mean square for carbon and the mean square temperature, that we should just get n. 4 times n, and this one would be 0 for no effect. Right? And so depending on the sample size, you get a larger sample size per group with these effects and this variance that was 4. That's kind of the residuals. The more sample sizes, you can get significant effects to show that they're significantly different. Right? It doesn't change the, under this, if nothing else changes, the average estimates are going to be kind of plus or minus 1 for carbon, plus or minus 2 for temperature. If that's a big impact in the context of the measurement of how much variability there is in the steel, that's what we would get. Right? So we would test these based on an F statistic. Right? So the degrees of freedom for the F distribution, there's 1 in each numerator, and 4n minus 4 in the denominator. Right? So these would be, you could figure out for different values of n, would it be significant if you did this kind of study. Right? But we can augment this. Right? You can take the same thing, but then add in an interaction. Right? And often, sometimes the interactions are big, but they typically, I think of them usually as being smaller than the main effects. Right? So let's think about what if there's an interaction between temperature and carbon levels. There's an interaction with these things on how they impact the steel strength. Right? So to specify an interaction like this, there's carbon and temperature. Right? And we're going to put numbers in there that add up to 0 that specify how they go. So this is low and high, and low and high. So let's say low carbon and low temperature, you get 0.5. You want to make these things add to 0 by rows and columns. Otherwise, it could be put into the main effect for those things. So this would be one way of specifying the interactions. So our graph that had what was on the axes, it was carbon, right? Low carbon and high carbon in this example. And then low temperature was the better one, and high temperature was not as good, right? So for any combination of these things, you would take the 100 plus the low carbon effect. So 100, low carbon was -1, high temperature was -2, right? And then what does the interaction say? Low carbon with high temperature would be another -0.5. So low carbon, high temperature is another one. And so that one is going to come out to be not 97, but 96.5 as the interaction. This one, if you do the similar thing, becomes 101.5, because it was 101 before, but low carbon with low temperature gives you a boost. Right? And then these two, this is still higher, 102.5, and this one is a little bit higher, 99.5. So it's not easy for me to draw it just kind of freehand like that, but the difference here is 5, whereas the difference here is 3. So it is supposed to be narrowing in, right, to kind of illustrate the interaction. So now we would have a sum of squares for interaction. Right? That kind of illustrates how the means would go. The sum of squares for interaction is now going to be is actually n, right? That what there is there's n per group, right? And so the deviation of this from the kind of main effect is either 0.5 or -0.5. So we're going to have n times 0.5 squared plus n times -0.5 squared plus n times, the other one's -0.5, and then n times 0.5 squared, and that will add up to just n. It's 1/4, 1/4, 1/4, 1/4. And so we get that as our thing. Right? Nothing else in the table changes. We end up with mean square for interaction being just n, because there's 1 degree of freedom for it. And the F statistic for testing the interaction ends up being n over 4, because the mean square error was 4. Right? So the interaction is a low, kind of a lower magnitude. So it ends up meaning for it to be significant, we're going to need a bigger sample size to prove it. There's some value, I suppose, in going through at least one where you kind of build up the, what does it look like if there's a main effect of this, or this one's a little different, and then an assumption about the errors and sample size, and it kind of works out, right? So let's take a look at a simulation that looks at this. Right? And that's on the code for today. So I'm going to follow some of this advice of getting certain contrasts in there for looking at plus or minus things that won't really impact things too much. And so I'm going to simulate some data. So I set some number seed, 10 observations, carbon effect, a certain temperature effect, and then some random errors for the standard deviation of 2. Right, so what this, make sure that's set. And so it's going to create a data set, and then I'm going to add the carbon effect plus the temperature effect plus this. Now, I could add in 100 to it. It won't really affect any of the variability, right? It's just an average difference. Right? And so what that data set looks like here is it has the, the carbon effects, 1 or -1, the temperature effects, errors, and then you add those together and you get y. If you add 100 on it, then it would be kind of on the average 100 scale. And after you do that, you could look at what the differences look like. I knew that was going to happen as I was pressing the button. The box plots, right? So there's low temperatures are lower, higher temperatures are higher, or high carbon, carbon, high carbon, and then low temperature, high temperature. The L's end up looking like, ones or something, right? So, and if we did an analysis of variance on those, now we didn't put any interaction in there, right? But there ends up being a little imbalance in the y's, right? It's not perfectly at the mean. So just by random variability, you get a little bit of sum of squares for an interaction, even though the model had 0, but it's not significant. At this sample size, the carbon and temperatures are very significant. And we could kind of refer back to our simulations, right? That little work that we did. Is this kind of what we would expect? So we expected this F statistic for carbon to be, so probabilities associated with an F distribution. We imagine that to be about n. So n per time was 10 in this. So we imagine our statistics is going to be about 10 for an F value. That's a pretty big F value generally. Well, I guess we got 20, so we ended up a little bit more. Right. And this is interaction. So degrees of freedom would be 1 and, all right, so we need the upper tail, so it's 1 minus that. And the degrees of freedom for the interaction were 4 times that 10 minus 4, or 36. And so we expect pretty small p-values. We actually got something a little bit bigger by chance, but anyway, it's consistent generally with it. We anticipated being significant because of the kind of little work that we did. And the interaction is not significant. What if you only had 5 though? Right? You can run 5. Here's some data, and make the new y, and here's the box plot of those. Right? With only 5 observations, you can get kind of some funny looking things. The spread is supposed to be the same in all these cases. Right? And if you summarize these, it happened to come out with one of the effects is not significant. Is that what we anticipated? Well, we would just get 5 as the expected value of that. It's a much smaller F statistic. Degrees of freedom would be 1 and then 4 times that much. We would expect p-values about 0.04. So even with 5, we kind of expect it to be still significant, but it's closer to borderline. And in this particular simulation, and honestly, I tried a couple, and it ended up with one that was not significant. Again, the interaction, there's a little bit of sum of squares for interaction, even though we know theoretically, in terms of the model, it's 0, but it takes up a little bit there. We can do pictures. And, so this is just an example of coding to do that, and I'm sure there's different ways to do it. And if you use some of the fancier graphics packages, it can probably be nicer. But if I just split the y's according to carbon and temperature, and means, I get this little means, okay, then plot it. Below, for carbon's on this level, carbon value is -1 or 1, so it's not labeled as L or C, it's labeled as -1, 1. So it puts it at those values, and then, but I have put symbols in here for the those others. Right? So you see that effects. No, they're a little bit different apart, but no significant interaction there. With 5, right, which one? The carbon was not significant. So there is a difference, a slight difference. It's a little bit different, but given only 5 and the variability is not significant. You can look at different contrasts. AOV is another way of doing analysis of variance instead of the ANOVA. And one thing it has is it will give a standard error for a contrast. You kind of have to tell it you want the carbon level versus the first carbon level versus the second carbon level, and some coefficients in there. But anyway, there's a way to kind of estimate that average difference. You get an average difference of 0.53. What is that? You take the mean when the data is -1 versus that. Everything's balanced, so it's fine to just take the mean differences. That also gives us, oops, that's not taking something different. -2.58. Well, that's a standard error, right? What is the standard error of the contrast? Well, back in the ANOVA, right, we had, when it was n equals 10, we had a mean square error of 2.86. Right? So that's sigma hat squared. Right? So the contrast that you might like to look at would be the square root of that. There was 20 per group. Well, there's 10 per group. Right? So there's 20 at each level of that. And then there's a difference of 2 groups. So you get a 2 through there. And that's the standard error. So if you take the mean plus or minus a t-value, again 40 in that sample minus the 4 different combinations of levels, and then this is sigma hat once you take the square root, and then this contribution there. And so we get a 95% confidence interval for the difference. Right? And carbon was significant when n equals 10, so that interval doesn't include 0. You could do that for 5. Would it include 0 or not? Right. We just did a contrast between carbon, with the data set being 5. Now, the sigma hat squared, the mean square error was a lot bigger. I guess I made the variance bigger in that one as well, just to help it be not significant. And so anyway, we get a confidence interval that does not include 0, extra minus. You can do other things, like you can say, are these 2 things different or not? Right? You can contrast this mean versus this mean if you're interested in doing that. Right? Or you can just do, are these 2 means different, ignoring those 2. Right? This one does the contrast of these 2 middle ones, and it turns out that they're not significantly different from 0. I wanted to look at a couple other examples just to illustrate other things about doing this. And so the first example comes from this book by Fairway. There's a data set in there on sexual abuse and post-traumatic stress disorder. So, serious topic that needs to be studied. And these are a data set here. And this data set, when I type library, then it's included in that library as part of that book. I've loaded it before, and it's in my library up there. So there's 76 observations on three variables. The variables are the PTSD, post-traumatic stress disorder measurement. So that'd be based on a scale, asking many questions, evaluating, maybe in a clinical setting to judge the level of PTSD. And then a report of childhood physical abuse and sexual abuse. It looks like it's also CSA is, I did not attach that. I think just refer to the variables. Is these abused or not abused? So that's just a binary variable. The scale measure of childhood physical abuse, though, is numerical. Just around childhood physical abuse. Oops, get back up here. Is more like this. You could create a factor by saying, is it below a level or above a level, cutting it somewhere in either kind of, into 2 or 3 groups. Doesn't appear to be an obvious place to cut, like low, high. But this is really illustrating this analysis of covariance, really. So if you look at, is post-traumatic stress disorder differed by sexual abuse category? And yes, it looks very significantly different. You can do things like this little tilde notation. It looks like the default is that box plot. But if you want to, you can augment this by, well, PTSD versus CPA, the physical abuse. That's going to be a scatter plot, right? But you can put a character in here to indicate yes or no for the sexual abuse as well. And so down there. So this plot gives you one like this. So it's the physical abuse measurement versus post-traumatic stress disorder, and there's this going up. But there was abuse and no abuse. Right? And so in this picture, there seems to be possibly different relationships. There's a difference between abuse and non-abuse. We know from the box plot that abuse has higher levels of PTSD, right? Which is it's a sad example, but it's important to study things if you needed to predict this, right? You might have some variables and need to predict or try and make categories for different purposes. But kind of trying to look at this, maybe the A's are up here and the N's are up here. Is there a similar relationship, right? Is it kind of just parallel, or is there kind of an added terrible effect of having abuse, right, on sexual abuse? So you can look, is there a difference between PTSD based on the CSA abuse levels? And yes, there's a highly significant difference there. If you run a regression of PTSD on the CPA, on the physical abuse measure, those are quantitative, right? So there is a significant effect here. The plot there, that's one line, right? When there's no groups are in there. But most of the A's are above and most of the N's are below. Right? That would suggest there'd be a difference. So if you do a residual plot based on that model, and you clearly see the A's above and the N's below, so that's going to suggest that maybe 2 lines are there. Residuals kind of have a little bit less than normal, maybe there's kind of a clumping effect there. So you could put in the effect of one of these variables, both variables, and they are both highly significant together. The residuals now don't look like there's quite as much 2 clumps because you have an effect for each group in there as well. And if you put the fitted values in there with the letters, right, here's the abuse predictions, and the ones that did not have abuse, their predictions based on their CPA level. Right? And this model has the parallel lines. So this is a constant distance all the way along here. But it doesn't seem to kind of off-centered from the plot a little bit. Maybe there's an interaction between that. So this, you can look at ANOVAs, and one thing I noticed, so this is ANOVA for just the CSA, the 2 categories. The CPA is significant as ANOVA. If you put them both in, you get significant effects here. But it seems like that R, with the particular effects, the certain effects, is computing slightly different things for these two things. Like this, the sum of squares, residuals is the same in both are significant, but it looks like it's what it's reporting is the sum of squares if you only had CSA, and then kind of the decrease in the sum of squares if you add the next variable, right? And so it depends on which one you start with. The CSA seems to be, the sexual abuse indicator seems to have more of an initial effect than the physical abuse quantitative measure. So I think if you change these, right, if you use a nested test, you could get kind of the overall effect of one of these variables or the other. But, right. So yeah, so the interpretation becomes that one is the significance test of just the first variable, and then the next one is the effect of the second variable given that the first one's in there. So more of a stepwise. So I might look into that a little bit more. But is there an interaction? Well, it's the same type of model with this thing in here, right? Is there a significant interaction? And it turns out that no, there was not a significant interaction here. This line would be testing is there a significant interaction. The ANOVA for that gives us the same p-value for testing that interaction since they're one. You can do a confidence interval so the effect of interaction, that would be a change in slope is centered at 0, so it's not significant. If you do a little bit of plotting, right, so these are, maybe I'll just add it to that and make it red. So these are going to put the predictions, the fitted values, under the interaction model. How do they show up? They don't change too much from the parallel lines. So the effect doesn't seem to be significant. Right? So they seem to be two different effects. Important to measure both and measure them separately. In terms of the outcome. So that's what you get with an ANCOVA. You get a quantitative variable and you get this difference. Right? So I wanted to look at one other example to finish out today. This one is about tooth growth in guinea pigs that are given vitamin C or orange juice. Right? So not the same weight as the others, but in terms of childhood health, right, extremely important. If children are living and are deficient in terms of vitamin C, and that affects the growth of their enamel and their teeth, and they end up with rotten teeth before their permanent teeth are coming in, and they have to be pulled, and it's terrible for their health. So all those, it's studying, this is a data set in R, so it should be there. This has the length of the teeth that are growing, and do they get a supplement, and the dose of vitamin C that's there. So this is a file, a health file in here. 60 guinea pigs, some of them receive 3 doses of vitamin C by either orange juice or ascorbic acid. So there are 30 getting each type of administration of this. The doses are 0.5, 1, or 2. And there's 10 every combination, so it's all balanced. And we can look at the length as a function of these couple of things, right? So the OJ, of course, is orange juice, vitamin C, ascorbic acid, and then the dose levels, like this, what do you see? Big impact of dose. Is there a difference between OJ and vitamin C, the ascorbic acid pill? Because kind of at every level, well, these two are kind of different, right? So maybe there's something going on, but it's not as striking as just the dose effect. Right? And if you reverse these, right? If you reverse the order that these things get put in here, right, you see it the other way. Okay. Oops, I didn't want to run it. So here's the OJ, here's the 0.5 dose, here's the 10 dose, here's the 2 dose. So it kind of looks at lower levels of dose. The administration seems to matter, like the vitamins. The OJ seems to do better than the pill. But once you get up to a certain dose, it doesn't seem to make a difference. So that's kind of looking at it different ways, you kind of see possible different things. Right? But then we got to test. And I'm just going to jump to testing, is there an interaction between these things? Well, I guess we could see the NOVA, LM, is the link, dose plus the supplement, are both of those things significant? And yeah, both of them are statistically significant effects. There's an adequate sample size, 10 for every combination, 60 altogether. Is there an interaction effect? And so this would be the small model, which has an additive, and then the larger one that would have the interaction. And yes, there seems to be an interaction effect in there. If you do it as a linear model, you get an effect for dose, an effect for supplement, and an effect for this. So how is R treating dose in this? Dose had, right, 3 levels, right? But there's only one coefficient for dose. Right? And back in that ANOVA model, it only gave, well, one degree of freedom for dose. So it's treating dose as a quantitative factor. It is quantitative, right? But it's treating it as quantitative, not as 3 different groups, right? Is that a good idea? Is it good to say that there's a linear relationship with dose? So sometimes mixing the categorical and things gets a little subtle. You have to pay attention to how it's being used. Right? One other way to do it is to do factor as a dose as a factor variable. Say there's low, medium, and high, which effectively would do that, right? Low, medium, and high. It's not labeled LMH, but it's you tell it to do as a factor, it will treat that as a factor. So if so we're investigating how R treats dose in this, right? It was scored as 0.5, 1, and 2, so if you just put it into the model like this, R is treating it as quantitative, right? And not as low, medium, and high. But you can force it to. So right, if you did this, well, let me do this one. I would do summary of LM, and then length is a function of as a factor of dose plus the supplement. It will give the impacts of dose 1 and dose 2. The third level is, would be higher, and then there's a supplement. Dose 1, dose 2. Let's just see what this, I want to look at one thing. Right, so it has the levels 0.5, 1, and 2. Dose 1, 2. Just wondering why this is positive in comparison, because I think that these would have to be higher. But anyway, we can think about it. I wonder about that. But anyway, there could be an interaction. If you multiply these things together, right, then there's going to be an effect for supplement or not, effect for 2 of the doses. Right. Then there's going to be 2 more things for interaction. It has to add a couple more things in there. So if that runs, it goes off screen here, but the p-values, there's not detail there. So some of the interactions are, well, these 2 are not quite significant in there, 0.25 and 0.09, but maybe together they add something. So let's see. So this ANOVA, well, let's see. I didn't exactly do that. Now that I'm asking that question, what we can do is put in, if we do ANOVA, an LM that has length as a function of as a factor of dose, plus the supplement is going to be an additive model. I want to just see what that is. That is highly significant. And would it be better to do there that, right? Would it be better to do that or add length as dot factor of dose, right, times the supplement and get an interaction when dose is treated as a factor? And yes, it still says that it's significant, right? So, but when we looked at the effect of either one, they didn't look significant individually, but kind of the combined effect could still be significant. So that's kind of interesting, actually. So you need to look at it as a whole thing. So now the question, how should we treat dose? Should dose be quantitative and have a linear effect, right, like a line? Or should it be as a factor, right? As a factor, you're not constrained to 0.5 times beta, just, 1 times beta, 2 times beta to get that contribution effect, right? It can more bounce, right? So this model here has dose type supplement, dose here is quantitative, and this is the factor one, right? Which model has more parameters? Which one's bigger? The second one's bigger. Right? The second one has to have the effect of, there's 3 categories, so it has to have 2 coefficients to have the effect of dose, right? The linear one, you just multiply dose times 1 coefficient. So this one's bigger. That ANOVA suggests that, the linear model is not good enough, right? That you should have this flexibility. So I'm going to plot the data a little bit differently. Right? So this length is here and dose is here. But I'm going to add a little bit artificial offset by category. Right? It would really be 0.5 and you couldn't tell the 2 groups apart. But if I add just 0.1, it's at dose 1, but I'm just kind of offset it so you can see it. Right? So these are the two treatment methods. Here, I'm going to add the printed ones when it's quantitative. When dose is a quantitative one. There's a linear prediction, right? So the linear goes here and then up here. And there's an interaction, so they have different slopes, right? How does that fit the data? See any place that it seems a little bit inadequate?
Seems pretty low for the one dose for the.
Maybe even for both groups,
Yeah.
right? This looks pretty good, right? This looks kind of in the middle here. This one is kind of in the middle here. It's kind of more spread, but it's kind of in the middle. Right? So it looks kind of okay here, but going linearly, it kind of misses the center of those points. So maybe the response is nonlinear. Maybe it's quadratic, right? That as you get, if you gave these guinea pigs 6 grams of vitamin C, maybe it's just going to level off. Their teeth aren't going to keep growing. There's some limit to that. So let's put the linear, what do I call that, F, in there at the factor version, and put the plot there. Right? So the F's are where the predictions are for the factors. And everybody in that group gets the same prediction because there's only certain levels, right? So these are about the same. These are definitely higher, more in the middle, and these are in the middle of those, right? So the factors are really moving these primarily. You're getting a significantly improved fit because you're matching those better. And also this one, maybe. A little change there. But if that is quantitative and more quadratic, we could make it quadratic, right, in regression. So dose interaction versus dose times dose squared. You can fit those things. And it's significantly better to have a quadratic than a linear. And here dose is all quantitative, but it's quadratic. And if you summarize this upper interaction is not significant. So maybe you don't need an interaction with both the slope and the quadratic term in the model. Maybe they don't need separate quadratics. Maybe you can reduce a parameter and be a little bit better. And so that's this next part. Dose times summary has an interaction, and there's a quadratic effect that affects both. A little bit kind of a reduced model, but right. So that's gives this model everything. All the predictors are significant, which is nice. R squared is about as high as any of the other models. But the other one got up to 0.79 or something like that, but it had that extra term in there. And if you put so Q is going to be for quadratic, and I'm going to be purple, so I'm going to put those fits in there from that model. Where do they show up? They show up basically right on top of the blue. Right? They're matching the blue quite well. So the blue one treated it as a factor and estimated more parameters to get every separate effect, but the quadratic one is this nice curve. The nice thing about this quantitative dose is now I can predict at 1.5. Right? When it's a factor, I don't have anything at 1.5, so I can't use it. But if it's quantitative, I can predict at 1.5. So here's the predictions at 1.5, and here's where those 2 points would go. New points in green there, if I decide to give 1.5, it's going to predict kind of in the middle. So two-way ANOVA, you have two separate factors, right? You can look at interactions. If you have a quantitative variable, you can do kind of interesting things. And so then we'll really take up some of the material more in chapter 14 on Wednesday. And I'll post a couple problems to work on, and I know I'm behind on a couple things. Catch up on grading. So. Yeah.
Thank you.
Now you have a data science class.
Yes, that's what I have next.
Yeah. So it's a little bit different approach to using R and the
Yes, yeah.
Jupyter notebooks. And
Funny you mentioned about the graphs, because just like for our project proposal, I was just quickly like graphing things. I wasn't worried about using ggplot, and like, I was planning on like, prettifying it before I turned it in, but I went to him for extra help beforehand. And he saw I just used a hist like comment, and he's like, oh, "You didn't use ggplot? That's sacrilegious." I'm like,
yeah, so no, pretty soon I'm going to be a dinosaur out here, not using all these things, and it's a it's also a learning curve, but it's I find that it's a question about visualization.
Yeah.
It's, how much more inference do you learn from fancier plots? And you do. Like, I manipulated plots, and you saw different things, right? And that's the tool. So, but right.
Yeah. All right. Have a good one.
Yeah.
Yo. What's up? Yeah, do an agenda too, I think.